Welcome back, ladies and gentlemen. So we are continuing our discussion on how evolution and the connection to allele frequencies is present. And ultimately, natural selection really is what brings about adaptive evolution. It's working directly on the organism's phenotype, as a result, indirectly working on those allele frequencies in that population's genotypes based on evolutionary fitness. So, when we define evolutionary fitness, you've often come across phrases like survival of the fittest or struggle for existence. And those are okay, but oftentimes they can kind of be misleading. Most species are not directly competing for resources. They're not fighting each other for them. It's just a matter of who's able to obtain those resources in their environment, whether it's food, shelter, mates, better than somebody else. There are situations where there is direct competition, but most of the time it's just a matter of obtaining those resources more often or in greater levels than other individuals with a different variation in the population. So when we look at those terms like survival of the fittest, when we're talking about evolutionary fitness, it doesn't necessarily mean that it's connected to brute strength or anything like that. Instead, it's really a matter of just being able to obtain resources better than somebody else, and not only just obtaining those resources for survival's purposes, but also being able to out-reproduce somebody else, because theoretically you've got enough resources to do that. So it really is a matter of relative fitness. It's the combination of your genotype from one generation to the next that's getting altered because natural selection is choosing for a particular set of phenotypic traits. So a couple of things to keep in mind when we talk about natural selection, especially at a microevolutionary scale. Natural selection is working on a phenotype, not a genotype. Natural selection works directly on the traits that are physically being produced that allow them to survive and reproduce better. Those are definitely connected to their genotypes and the sequences of A's, T's, C's, and G's in their DNA, but it's not directly where natural selection is working. It's working on that phenotype, the physical expression of that set of instructions instead. And keep in mind the whole organism is subject to natural selection. So when we talk about relative fitness and we're focusing on particular alleles, it gets a little more complicated than that because we are dependent on the entire genetic and environmental context for which that trait is expressed. I can't just weed out your entire self and be able to focus just on your hair color, because your survival is dependent on a lot of characteristics that your body expresses, not just that hair color trait. So we're taking that sometimes out of context when we're studying the way in which microevolution affects allele frequencies, but we have to take a step back and recognize that it's really nature selecting for the entire organism collectively that is either being determined as successful or not. And so that's going to drive what gets passed on to the next generation. And there are cases where alleles or even pieces of DNA may contribute next to nothing to the organism's success, or may even be slightly maladaptive, but continue to perpetuate in the individuals as a whole, because again, we're taking that individual overall and the fitness of that individual's ability to obtain resources and reproduce better than someone else. So there are certainly going to be instances where a particular set of individuals may continue passing on what we would logically assume are poor traits, just because collectively as a whole they're more successful. And so it's not about survival alone, right? It is about reproductive success. So keep in mind that relative fitness can be zero, even if that organism is big and strong and seems to have great camouflage, or whatever the case might be for that organism's survival. If it can't reproduce, then it doesn't matter from an evolutionary standpoint. So if an organism is sterile, for example, that organism is not going to be able to contribute genes to the next generation, and as a result, from an evolutionary standpoint, isn't contributing to natural selection, and thus their fitness would be considered a zero. A mule is a great example of that. So it's a cross between a donkey and a horse. Mules are incredibly good horses, work organisms for us. They're big, they're strong, but they're sterile. And so, at least from a biologically natural selection standpoint, their fitness doesn't matter. It's zero because they can't pass those traits on to their offspring. They can't have offspring at all. So when we look at natural selection and we want to start modeling out how these genotypes are getting passed on from one generation to the next, selection is always going to favor certain genotypes by acting directly on those phenotypes. And so we get these three major modes of selection: directional, disruptive, and stabilizing, based on how those shifts in those genotypes occur from one generation to the next or over a multitude of generations. So basically we're looking at bell curves where you've got your most recessive on one end, your most dominant on the other, and then your most sort of heterozygote, if you will, in the middle. And when we get a situation with directional selection, we're favoring individuals at one end of that phenotypic range. This is most common when a population's environment changes or members migrate to new habitats with different environmental conditions than the previous one. So we're assuming that our original population has evolved to have the highest abundance in that phenotype in the middle of that bell curve, because that should have been what was most successful based on that set of environmental conditions. Didn't mean that the variation disappeared completely, but most individuals with that median set of traits were the ones who were successful in reproducing at the highest level. We move into a different environment and those environmental conditions are changed, or just the conditions in that population change in their environment anyway. And so we shift to perhaps a different variation in the population. So this one just happens to look at mouse color. Presumably they were blending into their environment. If something caused that environment to suddenly, and when I say suddenly, over long periods of time, geologically speaking here, their environment shifts to be more darker in color, then we would expect that the overall frequency of that darker coat color should show up. This is another one we also see in antibiotic resistance, right? So the more we use antibiotics, the more and more we're selecting for that more resistant portion of the population to survive and reproduce, and so we shift the average to that more resistant population. The more we use the antibiotics, the more we continually push that population to be more and more resistant to that given antibiotic. Disruptive selection, this one will now favor them on both extremes. This is often a situation where we're looking at early stages of speciation. Something has occurred where individuals at either end of the phenotypic range are being more successful than what used to be common and popular, used to be most successful. And if disruptive selection occurs for long enough and that split continues to occur to the point where either end of that extreme no longer mates with each other and perhaps cannot mate with each other after successive generations, then this could potentially lead to a speciation event, in which case both extremes now become their own species. And then stabilizing selection, this one occurs when we're looking at taking what is common and selecting for it even more, so it's becoming more and more common. Sort of reduces variation as a whole and maintains kind of what your text calls the status quo for a particular characteristic. We'll often see this in predator-prey interactions, where we've got one predator going after sort of the smaller, maybe organismal side of the prey species, another predator going after the larger end And so those who are sort of in the middle seem to be the ones who are most successful because they're not getting eaten by either predator. Another great example of stabilizing selection is average human birth weight. Historically, we would see most average babies being somewhere between 6, 7, 8 pounds. And if you think about it, that should hopefully make sense. The smaller end of the spectrum usually ends up meaning that there's something that has occurred, either premature birth or just low birth weight in general because of nutrition or other maybe genetic factors. And so the likelihood of that those smaller babies, less than 6 pounds, having what they need to be able to survive in terms of birth weight, because most babies actually lose about 20% of their birth weight within the first 24 hours of being born, they don't survive. The other side of things, being too big, becomes a bigger problem for the mother and baby getting stuck in the birth canal because the baby is just too big to get through. And so now we end up having a situation where not only does it become a problem, but at least before modern medicine, it was potentially deadly to both baby and mom, and so we would select against that as well. So it's interesting to actually see how modern medicine C-sections, medical interventions now are actually shifting the trait here and actually giving us more of a directional selection to higher birth weights. Because once again, having that slightly higher birth weight seems to be beneficial within reason, because that baby ends up losing some weight right after birth. So historically, we've had a stabilizing selection to have that average birth weight be kind of in the middle, but now with modern medicine, we're actually shifting that size of an average newborn to actually being slightly larger. So if you take a look, this is just kind of taking what that original population would look like with these phenotypes of fur color and just giving you examples of how those different selection modes would look from a graphical standpoint.